In this final video for section 7.4, we're going to be looking at what we call octet rule exceptions, and we're going to be linking that back into the concept of resonance and formal charge. So nitric oxide is often formed in high temperature environments, for example, what you'll find in the engine of your car. And in these kinds of environments, there's enough energy to break the strong triple bond that is present in the N2 molecule. So oxides of nitrogen are notoriously reactive, and NO further reacts with O2 to form NO2, and that'll continue reacting with water to ultimately form nitric acid. So oxides of nitrogen are really bad for your breathing and your eyes, and they're the principal cause of what we call photochemical smog, which is this brown haze that you see over polluted cities, particularly in the presence of bright sunlight. That's why it's called photochemical smog. So you're more likely to see this type of smog in Los Angeles, where it's kind of nice and warm and the sun's kind of intense, rather than in New York. So this brown haze is typical for pollution found in warmer places. Now, the presence of nitric oxide in the atmosphere, as I said, it reacts with oxygen and then it can further react with water. Ultimately, it results in the formation of nitric acid, which is a cause of acid rain. So the interesting thing about NO is that it has an odd number of valence electrons. Nitrogen's in group 5. Oxygen is in group 6, so that gives us 11 electrons. So what we recognize here is that in this case, it's not going to be possible for both of the atoms to end up with a complete octet. It just doesn't have the correct number of electrons to allow this to happen. So the first octet rule violation we're going to see is for odd electron molecules. And NO is the classic example. So one atom in this molecule is not going to get an octet. It's going to end up with less than an octet. The question is it nitrogen or is it oxygen? So we're going to draw the Lewis structure of NO. As we mentioned before, we get 5 electrons for the nitrogen and 6 electrons for the oxygen, and that gives us 11 electrons total. Nitrogen, we're going to treat it as a central atom because it's in group 5, whereas oxygen is in group 6. So our basic structure is going to be this guy. So that uses up 2 of our 11 electrons, leaving behind 9. Now we're going to complete the octet on our outer atom by placing 3 lone pairs on there, and then that leaves 3 electrons left. So those 3 electrons get placed on our central atom, and then that leaves the nitrogen with 1, 2, 3, 5 electrons around it. So we bring in a lone pair, and that puts a double bond there, and that gets the nitrogen up to 7 and the oxygen with a complete octet. Now, couldn't we also give the nitrogen a complete octet and leave the oxygen with 7? I mean, that would use up all 11 electrons as well. 2, 4, 6, 8, 10, 11. I mean, they both work, and they both have one atom that doesn't have an octet and one atom that does have an octet. So the question becomes, is one better than the other? What atom is going to miss out? And we're always going to have this choice when we can't give every atom an octet, is what atom ends up without the octet. So let's have a look at the formal charges for the 2 possibilities. Here's the nitrogen, so we're going to do 5 minus 1, 2, 3, 4, 5. That gives 0. Here's the oxygen, 6 minus 1, 2, 3, 4, 5, 6. That also gets 0. That's a very good Lewis structure, right? Everything is 0. Let's have a look at this guy. I like that one, right? There's the nitrogen, 5 minus 1, 2, 3, 4, 5, 6. gives me -1, and then 6 minus 1, 2, 3, 4, 5 gives me +1. So that one, not so good. So it seems like it's best if the odd electron goes on the nitrogen and that the oxygen has the complete octet. So molecules that possess an odd number of electrons are known as free radicals. They don't like it. You know, we've got atoms there where someone doesn't have a complete octet. And as a result, they're highly reactive. They're going to keep reacting, and they are going to hopefully find a more stable configuration. These free radicals are, rumored to be very, very damaging to biological tissues because they're so reactive. And now what happens with NO is, you see this odd electron here? It wants to pair up with another one. So what happens pretty quickly with NO is when two molecules bang together with the correct orientation, they undergo this process of what we call dimerizing, which basically means that they form a covalent bond between two of them. And then in that way, in the N2O2 molecule, everybody has an octet. These two nitrogen atoms that previously had 7 electrons, now we've got 2, 4, 6, 8, 2, 4, 6, 8. Everyone's got an octet. So this NO is a relatively short-lived thing, but what we do know is that the nitrogen end of the molecule has the odd electron, and that's going to be the reactive end because it wants to get that odd electron paired up. Okay, so that was our first octet rule exception. Now we're going to look at this molecule here, SF6. So sulfur's in group 6 gives me 6 electrons, fluorine's in group 7, and we've got 6 of them. So you add all of that together and you get 48 electrons. Now, as sulfur is in group 6 and fluorine's in group 7, sulfur's going to go in the middle and all the fluorines are going to go on the outside. So to get the basic structure, we're going to use up 2, 4, 6, 8, 10, 12 of our electrons. So 48 minus 12 leaves me 36 electrons to finish everything off. So I put lone pairs on all of my outer atoms until they all have an octet. And so that's going to be 6 lots of 6, or 36. So 36 minus 36, no electrons left over. So step 5 is not needed. There's no electrons to place on my central atom. And what have we got? When we look at the central atom and consider whether it has an octet, 2, 4, 6, 8, 10, 12. Sulfur has a share of 12 electrons. We say it has an expanded valence shell. And we will see this sometimes, and we've already seen it in some of the homework problems. So sometimes the second class of, so we've got odd electron molecules is one example of a octet rule exception. Now we're seeing the second one, expanded valence shell, where we have more than 8 electrons around our central atom. Now, when, is this a good, we're only going to see this with the formal charges work. So if we look at the formal charges on the sulfur here, sulfur's in group 6, minus the non-bonding electrons on 2, so that's the number of bonds, 1, 2, 3, 4, 5, 6, minus non-bonding electrons, there aren't any, 0. So the sulfur has formal charge of 0. And then if I look at the fluorines, I only have to look at one of them because they're all the same. Fluorine's in group 7. There's one bond. And then we've got 2, 4, 6, 1, 2, 3, 4, 5, 6 non-bonding electrons. The formal charge on all of the fluorines is also 0. It's a great Lewis structure. Nothing wrong with it. Every atom has formal charge of 0. So this is a good good set of formal charges. In fact, it's the best set that we can get. So when are we going to know that it's appropriate to, or we might expect to see, an expanded valence shell? Well, all of these, attached atoms, they all take up space. So we're going to see expanded valence shells when we have large central atoms. And what we observe is that we only see expanded valence shells for central atoms from period 3 and beyond. And often we're going to see this when we're forming compounds with fairly small electronegative elements like fluorine, oxygen, and chlorine. So we haven't really related this a lot to formal charge or resonance yet, but now we're about to kind of jump in and go the whole hog and bring all three of these ideas together. So to illustrate this, we're going to look at the Lewis structure of the sulfate anion. So sulfur's in group 6, we've got one of those. Oxygen's in group 6 as well, and we've got 4 of those. And then we need 2 electrons for the charge. So you add all of that together, and you've got 32 electrons to work with. So now, oxygen and sulfur are both in group 6, but sulfur is lower down. So what that means is that sulfur is going to be our central atom, and then the oxygens are going to be our outer atoms. So to attach the oxygens just to get the basic structure, we need to use 2, 4, 6, 8 electrons. So 32 minus 8 gives 24 remaining. Now I'm going to complete the octets on my outer atoms by adding 2, 4, 6 in order to get them up to 8. So I've got 4 of them, so 4 times 6, I'm going to use 24 electrons to do that. So 24 minus 24, I've got no electrons left. So in step 5, I would put any leftover electrons on the central atom. I don't need to, because there are none left over. And then step 6 is, if my central atom doesn't have an octet or higher, I'm going to bring in lone pairs until it does. And again, if I check the central atom, 2, 4, 6, 8, I see that sulfur already has an octet. And so I wouldn't consider to bring in lone pairs to improve the Lewis structure. However, I know that sulfur has the capacity to have an expanded valence shell because it's in period 3. So I wonder what would happen if we expanded the valence shell of sulfur. So first of all, let's go through and do formal charges for what we've got so far and see if everything is 0. And when I do that, what I find is nothing is 0, right? So all of the oxygens have formal charges of -1, and the sulfur has a formal charge of +2. So that's kind of like, maybe there's room for improvement. Maybe I could get some of the formal charges on these atoms down to 0. So what I'm thinking here is, what about if I expand the valence shell on sulfur by bringing in one of these lone pairs and making a double bond? Would that make anything better? So I go ahead and I do that, because this seems reasonable, because I know oxygen does like to make 2 bonds. So I'm going to bring in this lone pair here and make a double bond. And now look what happened. I'm going to leave all the formal charges on these 3 oxygens alone, because there's no need to recalculate them. Nothing has changed. But let's have a look at this oxygen. 6 minus 1, 2, 3, 4, 5, 6, 0. Woo, it worked. I got an atom down to 0 formal charge. Let's have a look at what happened to the sulfur. 6 minus 1, 2, 3, 4, 5. It goes from +2 down to +1. So it's better, right? I got one of my oxygens down to 0. I also got the sulfur a little closer to 0 as well. So the question is, if it worked once, maybe it'll work again. So let's bring in another lone pair, all right? And then now what we've got is we've got these 2 doubly bonded oxygens. So the formal charge on this guy, 6 minus 1, 2, 3, 4, 5, 6, also 0. Don't really need to calculate that because it looks exactly the same bonding pattern as the one that we already figured out with 0. I haven't changed these 2, so I can leave them alone. And then now I'm going to recalculate formal charge on my sulfur. 6 minus 1, 2, 3, 4, 5, 6. I got that guy down to 0. So now I've gone from having no atoms having 0 formal charge to 3 of them having 0 formal charge. So that's really working. All right, if it worked twice, maybe doing it a third time, it'll be even better. So I'm going to bring in this one from the left now and see what happens, right? So bring these two guys in, make the double bond. I observe that it has the same bonding pattern as the other two, so that's just going to be a 0 there, 0 there, 0 there. Nothing changed there, so I'm going to leave it as a -1. But I've got to recalculate for my sulfur, so it's going to be 6 minus 1, 2, 3, 4, 5, 6, 7. And that gives me -1. Now this is no good because oxygen is right next to fluorine, sulfur is further away. Sulfur has a smaller electronegativity than oxygen, so it should always have the more positive formal charge. It doesn't. Its formal charge is more negative than 3 of my oxygens, so that's a bad structure. So the best one would be that one, where I have 2 single bonds and 2 double bonds, and obviously you could imagine that there are resonance forms where the double bonds move around the structure. So for sulfate anion, expanding the valence shell of the central atom improves the formal charges, and this is closer to the real structure of sulfate. So the thing to kind of keep in mind here is if central atom is period 3 or higher, check expanded valence shell. Because you just might be able to get a better Lewis structure than following the simple rules. Okay, so we've got a couple of things going on there now. We've got odd electron molecules. And then now we've got expanded valence shells. Well, we're kind of breaking the simple rules. What we're going to look at now is our third class of octet and exceptions, and they are what we call electron deficient molecules. So what we see is that for molecules with central atoms that are from either group 2A or 3A, so classic examples would be beryllium or boron, that sometimes the best Lewis structure is when the central atom actually has less than an octet. So a good example of this is electron deficient boron trifluoride. Now, if we followed the rules all the way through, we would recognize that in this molecule here, boron only has 2, 4, 6 electrons around it, and really we should bring in a lone pair and put a double bond there. Now let's have a look though at the formal charges of these two structures and see if one is better than the other. So boron is in group 3A, so we've got 3 minus 1, 2, 3, a formal charge of 0 on the boron. Each of the fluorines is from group 7A, and they're all the same, so if we figure out the formal charge for one of them, it'll be the same for all 3. So 7 minus 1, 2, 3, 4, 5, 6, 7. So the fluorines also have formal charges of 0. So this is a great Lewis structure, even though the boron doesn't have a complete octet. It's what we call electron deficient. Now, what about if we did do the correct Lewis structure? Would it be better? Would it be worse? Well, boron's from group 3A, so 3 minus 1, 2, 3, 4, we would have a formal charge of minus 1 on the boron. These two fluorines are exactly the same, so we only have to do the formal charge on one of them. Fluorines in group 7 minus 1, 2, 3, 4, 5, 6, 7. So they would have formal charge of 0. And then this fluorine over here is different, so we have to work out its formal charge. 7 minus 1, 2, 3, 4, 5, 6 gives me plus 1. Now this is very wrong because fluorine is the most electronegative element on the periodic table, so it should always have the most negative formal charge, and it doesn't. The boron does. So this is a terrible Lewis structure. So this is an example of an electron deficient molecule, which is our third class of octet rule exception. When we want to be on the lookout for electron deficient molecules is when our central atom is from either group 2A or 3A. Okay, so for homework I would like you to attempt these questions, and I'll be going through them with you on Wednesday's Zoom session.